Okay, welcome everybody. Today's lecture, NSA Part 2. I hope you watched the videos last time. I recovered, so I hope I can do the lecture today. So you learned about this interesting scenario from the book by Andreas Eschbach. And along the lines, in that book, he also introduces something that resembles a query language that's called SQL. SQL is the language for accessing relational database systems. So the video you watched hopefully talks briefly about the book and also introduces SQL along the way. So in the book it's called, yeah, it's kind of stupid. He uses a German translation for that, strukturierte Abfragesprache, which directly translates to structured query language. Yeah, that's SQL in German, SAS. And what he shows in the book is basically super similar to what, how SQL, super similar to SQL. Yeah, so I don't want to go through all of that again, so the errors, there are these 3 slides I promised in the video, and I promise you here again to show them to you as many times as you can't take those slides anymore, because they're so important and so many people get those slides wrong. So I'm briefly showing the slides to you now. Don't worry, towards the end of the semester I will show these slides again. Yeah, but it's really very common mistakes you should avoid. So one is this tuple access style, CRUD style, create, read, update, delete style access to databases. So basically use the database system or use SQL to access individual tuples. That is fine, that's one use case, but there's so many others. SQL can do so much more. And that's a common mistake. People argue you can only do CRUD style access. Well, there's so many more things. And then there's like all kinds of nonsense people mention in the context of SQL, like joins claim to be slow, which is completely wrong. Joins can join tuples on the order of hundreds of millions of rows per second. Yeah? So I don't think you will ever have a use case like that. So it's super fast if you do it the right way. And the third is SQL cannot handle more structured data such as JSON, objects, and graphs. Yeah, that used to be true back in the 80s maybe, but now it's 2024. Things have changed. SQL has evolved, and modern SQL standards. Yeah, so SQL is standardized. You can do everything with that. Yeah. Most people, though, still use SQL 92. Yeah? So 92 meaning 1992. It's a very old standard, which is already pretty big. Yeah? So we can't look at all of that. And then there's a 99 standard, basically, that's now very established, and many systems support that. For instance, PostgreSQL supports that. But there's so much more. Yeah? So it's insane. I think it's like if you print out the standard, it's like a bookshelf like that. It's totally crazy. Yeah? Okay, so you learned about the basic structure, the select from where structure, also how to read those queries. That's very important. So that's what I call the conceptual execution order. And always keep in mind, that is just for you how you read the query. What the database, what the system that processes the SQL query will do about that is a completely different story. So even though you read it in a particular order, doesn't mean it's executed like that. We will learn about that. Next week is a holiday again, but 2 weeks from now. And then the week afterwards, we will look at how those statements will be translated into efficient programs. That's called query optimization, and all database systems do that. And it's an art. Yeah? There's a lot of research going on in that field. So don't confuse that. This is just the how, the what. How do you want the result to look like? What kind of data do you want to have? But that doesn't make a decision on how that is going to be computed. That's very important to keep these 2 dimensions apart. Yeah? Yeah, and then there's this notebook using DuckDB. DuckDB is a fancy name for something that is a so-called embedded database that does similar things to what SQLite is doing. You might have bumped into SQLite. It's another embedded database. DuckDB is a little bit better with regards to analytics. It's a relatively new project, but has become quite popular in the past years. And we are also using it for our notebooks. Okay, so everything else was, joins, of course. So basically, you see the same things we saw in relational algebra now in SQL. Yeah? similar things, like we can do a join in relational algebra. Okay, how do we do the join in SQL? Yeah? We can do a group by aggregation in relational algebra. How do you do that in SQL? Yeah? And so it's basically, you could say it's kind of a different syntax you learned along the lines of SQL. Yeah? And we went as far in the lecture as to having clauses, so make sure you understand how that works. Here's a mapping to relational algebra. We had that on the slides. But it's the same idea as in relational algebra, actually with the same potential problems as in relational algebra. Yeah, so I think, yeah, I showed you this problem with a grouping key. You mustn't group, you mustn't output something that's not part of the grouping key. So here, this is this famous example where you group by experience, however, then output salary. Yeah, you see it here, and that's not allowed, except for special cases, but in the general case it's not allowed because then salary might not be unique. Yeah? So make sure you look at those examples, understand those examples, otherwise they may hit you hard when using SQL. Okay, yeah, that was it about part 1. Now we go on to part 2 today. Oh, I don't have to switch, cool. So back to our concrete application. So NSA, Snowden, and the global surveillance disclosures, the book by Eschbach, Data versus Metadata, links for further reading. So that's what we're talking about this week and previous week. And so we looked at this question 1, how do we phrase more complex queries? We can do that with SQL. Yeah? We looked at very, very simple examples in Jupyter. With DuckDB, our queries were like that. SQL queries can be rather long, yeah? Really super long and complex. Still, the system should be able to handle those queries. Yeah? Now we look at a little bit more at the transfer of the basics to the concrete application. Then we look at ethical problems today a little bit. And then next week, we look at, okay, what if data gets bigger? Yeah? Well, how do we actually get, as I just said, get from SQL to an efficient program, which is a very long story. For the moment, we ignore that. We just assume the system magically generates a program from that SQL command. Yeah? So we don't worry about that. So in the following, I would like to implement the idea that's spelled out on the first 40 pages or something of the book by Eschbach. So who actually read the book? Ah, cool. Okay, some of you. Yeah? So the problem is there's no English translation. I asked Andreas Eschbach last year, so sorry for that. Yeah, but he said that he didn't find a publishing house who would publish it on English, but maybe that's going to happen one day. But anyway, this is the gist of it. So the idea, and that's implemented, so if you didn't read the book, Helene is basically a main character working for the NSA, Nationalsicherheitsamt, in the book similar to NSA in the US. And she is basically programming queries, implementing surveillance ideas. Yeah? And the one idea, the central idea there in the book, that is, on average, everyone consumes about the same amount of calories. If someone buys on average much more calories than the average, this may indicate that she or he is secretly helping someone else, in other words, hiding. Yeah, so if you have a way to track how many calories are eaten by the people in your country, then you could conclude, or you could try to check the ones that eat more than average or really stand out and are outliers. That's the idea of the book, and that actually leads in the book to finding people that get hidden. So how do we answer this query? We first have to estimate the average calorie consumption of a person, then determine per household how many calories are purchased on average. As everything is connected, yeah, all this data is collected. Now you can join all of this data together. Join the data, do group by and stuff like that. Yeah? So I'm in no way endorsing that you should do that. This is just showing a bad example, or so I'm here to show you the problems with something like that. Yeah? Don't get me wrong. This is terrible. What's being done here? Yeah? I'm just trying to show. I want to make you aware of the risks. So then you determine the average calorie consumption per person in that household. Yeah? This is possible if you know how many people live in that household. And output that result list in descending order. Yeah, then basically you have an idea. Okay, the highest average consumption might be an indication that there's someone hiding. Yeah, then the next steps are carried out by SS in the book. Yeah? So really terrible. And then for us, as computer scientists, or you want to become a computer scientist, want to have a degree, at which step does the ethical responsibility of us computer scientists and data scientists begin? The book also explains that and plays with that idea. So the main character is always in doubt. Okay, should I really do that? My boss told me to do this query. Should I really do that? Yeah? And at some point in the book, Helene is really in between. Okay, she has to do what her boss says, versus if she does that, her boyfriend who's hiding will be found, yeah, and put into prison or even worse. Yeah? So the book explains that really well. Her responsibility and what she can do about that. And she will do certain things. I will come to that later on. But let's get back to the, as we learned first, the entity relationship model. This is the entity relationship model implied by the book. Yeah? Already a little bit improved. So from the SQL queries in the book, you can imply a model. We improved it a little bit, but that's basically all you need. So you have, let's look at it briefly. You have households here. Yeah, they have this artificial ID. They have an address part. They have a floor part. So address alone wouldn't be enough. Then you wouldn't be able to separate different apartments, kind of. So even floor could be questions here. If you have multiple households in the same floor, that wouldn't be enough in this example. Yes, you have to adjust the schema. That's a simplification already. Yeah? But basically, that represents the households. Then you have citizens with an ID as a key, first name, last name, birthday. So ID makes it unique. And then, of course, citizens can move from one household to another. So we have a live-in. And we have a start and until. So this is a relationship that's depending on time. Yeah? So once you move, you can move out and move to a different household. Citizens then purchase articles, and they purchase all kinds of articles. So we use that as a superclass here, and just show one subclass that is groceries. Yeah? So stuff to eat, and all these things come with certain calories. So calories per 100 grams, that's all we need as information to implement what's shown in the book. And yeah, so as you connect those two pieces, citizens live in households and citizens purchase certain articles, that is a problem. That is a problem here, that these two databases or these two information worlds, as you may coin them, are connected and can be queried from the same query. That is the problem in all of this. If you avoid that, everything is much better. Yeah? Yes, there still may be problems, and you will look at that in this week's exercises. But having that in a common schema and being able to query across very different use cases makes it possible to deduct certain information pieces. Right, so that's a note on attributes versus separate entity type. I think we alluded to that already in other use cases. It's always a discussion, okay, when is it an entity type and when is it an attribute? That's another example of that, so how you could do it differently. So here we did it by, we used this binary relationship type, citizens and households, and then I added start and until, like a time interval, to the relationship type. That's one way of doing that, but you could also do something like periods of time, make the relationship type ternary, and have the attributes here. Yeah, that's fine. Yeah? So I'm not saying one's better than the other, but when you translate, you see the following. So the translation of the first, I think that was a binary. Yeah, that's a binary. That will be translated as follows. So you have a live-in relation. Live-in, of course, you have foreign keys to to citizen, your foreign keys to household, and then you have start and until, and all of them form the key of that relation live in. In contrast, in translation of the seconds, the ternary modeling, you would have an extra relation just with those attributes. Yeah? That's what you could do, and then you can reason about, okay, do I really detect all of these problems that may occur? So for instance, what if time intervals overlap? Do I really detect that through the keying concept, or is it just if it's exactly the same thing? Yeah? So in the relational model, you would only see a conflict if you try to insert a period of time that has the same start and the same until data value. Yeah, then you won't be able to do that because that's a key over. Yeah? But if you have two intervals that overlap, yeah, you will be able to insert that, and maybe you don't want that. So you might have to worry about additional constraints if you implement that. Okay, so here's again an exercise for the ternary relationship type, just again to remind us how that works. So periods of time and citizens, do they determine the households? Yes, because we have a 1 here, so a period of time and a citizen together determine the household. For any given period of time instance, versus the interval, what I just said, a period of times may overlap different instances. So in theory, you may have overlapping instances. That's fine from the point of view of the model, but not fine from the point of view of the application. Yeah, so that's the trick here, the problem that might occur. So for a given period of time and citizen, there is either no household or one household, but not several. So max 1, this max 1 notation. A citizen can only be registered in one household for a given time. And then for the other two possibilities, household and periods of time does not determine citizens. Yeah, that's basically, again, this reading direction. This one towards this one, there's an M, no problem. The same occurs here. Citizens and households does not determine periods. Citizens and households does not determine periods of time, yeah, because there's an N. Yeah, so that's what we basically just learned. However, yeah, that's what I just said, but what actually happens if start and until periods of time overlap? Oops, yeah, so you break the idea or the modeling idea you had. So you might need to write down additional constraints. We had an example of that when we talked about entity relationship modeling. So it might not be enough to just keep the model like that, the entity relationship model like that, and translate it to the relational model. Maybe you might lose information here. Yeah? If you want to forbid that those time intervals overlap, you should write it down. Write it down, but for every translation, write down, hey, actually what I want is that they don't overlap. And then you can introduce extra logic to guarantee that. Okay. Yeah, so here's our model again. I think I showed that already. And what we do in the exercise, as I said, okay, the problem here is that these two worlds are connected, is you will look at two different models. So in the exercise, we use scissors and split the model into two models. And your job in the exercise will be to reason about, okay, are there still problems with regards to that? So if it's two separate worlds, and you can only send a query to either one of the models, or so the left part, you can only query the left part, or you query the right part, but not all of them together. Are there still possible problems, possible information pieces you may give away that were not intended to give away? Yeah? That is basically this exercise. Yeah? So what can possibly go wrong? Yeah? That's for this week's or today's assignment sheet. Yeah? And yeah, again, so if people talk about big data, so maybe you heard this buzzword term, and it sounds like big data is about large data sets. The data set we are using here for the notebook is like tiny. It's just a toy data set, a couple of dozen tuples. The problem with big data is not the size. The problem of big data is connecting dots, connecting databases, connecting information pieces that were not meant to be connected. That is the problem with big data. Yeah? The problem is that it's super hard, if not impossible, to foresee what kind of information you can deduce by connecting information pieces that were not meant to be connected. That is the risk with big data. Connect 3 different databases and you get insights no one could ever foresee. Yeah? That's the biggest risk with big data, and that's a prime example of that. Okay, so here's the relational model just for completeness. And now we jump directly to the notebook and to see how that works. So here's the notebook. It's on our website as usual. We're using DuckDB here. Maybe I restart the kernel. Okay, so let's import DuckDB. Yeah, then I create the schema, yeah, basically a one-to-one translation of the relational model. Then we prepared some fake data. I can hide, if I didn't say that again, whenever you develop a database system, I highly recommend you create some fake data for testing purposes. It gives you so much insight and gives you so much hints on how to improve your system. So we did the same here, some fake data. All the street names are fake and shouldn't exist. If there's any name you recognize, it's a pure coincidence. And then basically we have a couple of households here, for instance, these street and what's house number in English? I don't know. Number of that in that street and the floor number. Yeah? So that's basically the households. Then with citizens, we created even for that time period. Again, that's all random. Coincidences are pure random. We have this live-in relation. We have certain articles, potato and the unit. We have the calories per 100 grams information, and we have the purchases. So the amount purchased is here, and then the timestamp. And that's all you need. So then basically you can, through very simple queries, so this is not rocket science. So the techniques I'm showing were there already in the 80s. Maybe in the 70s you could argue. It's not some magic large language model you need to supervise people. I mean, if you who heard about this scary Windows Microsoft announcement about Total Recall? Are you scared? A little bit? Not even, okay. Yeah, so this is not as fancy as that. This is just a little bit of metadata and structured data and some SQL. Okay, so basically, again, so we split the data in different relations. Now we're connecting the dots. Yeah, we're joining it back. That's basically what we do here. So that's all we do. So we have a list where we join citizens with live-in and households. Yeah? And then basically we have for each name the household that person lives in. Here we count the inhabitants. This is done through a view. I highly recommend that you, so I could also write a statement like that, but that's hard to read. So it's always a great idea to assemble larger queries bottom up by creating views. Huh? And then typically you do something like that, drop view if exists. So if you ever had a view definition before, you just drop it, and then I recreate the view. And keep in mind, a view in SQL is really just an alias. Yeah? So I don't materialize any result. The database doesn't do anything except putting that into some hash table as an alias mapping. So whenever I refer to this symbol in a from statement again, basically this stuff here will be copied into this position as a subquery and then executed and sent to the system. Yeah? So nothing is executed, just when I do this, nothing happens. There are exceptions. In some systems allow you to do so-called materialized views. Did any of you ever bump into materialized views? No, okay, forget about it and never use it. Please never use it. That's a technique that was used for optimization purposes and introduced in the 90s. And at that point in time, it was a good idea. Today, the trade-off is such that I would say never use it. Please don't use it. They're different in the sense that if you write create materialized view, this result would actually be materialized, would be copied, would be stored physically on the system. And that leads to all kinds of problems. Yeah? One advantage, query processing, maybe the query time may be faster, but everything else is, you're in trouble. Yeah? So don't do that. Yeah? So just the standard dynamic views, or views for short. Yeah, that's what we do here. So basically for each household, now we know what are the number of inhabitants in that household through a simple grouping query. So here we group by the household ID over live-in, yeah, then we do a count star for each group. There we go. Then we can also show the corresponding address for each household and show for each address here the number of inhabitants. Discarding floors on the way. Now we count the calories per household. Yeah, for that we need information on the purchases. That's what we do here. You have to do some magic about this per 100 grams, whereas this kilogram stuff, have to be careful with the data. So that's a typical problem that when you integrate data, okay, maybe one relation keeps it in this unit, that keeps it in the other unit, and so forth and so forth. Yesterday I actually saw a clip from a British series about, I think it was about World War II and a convoy of military vehicles that wanted to go to a certain city, and they had to stop in the middle of the desert. They were running out of fuel, yeah? And then two officers were chatting about that, and then the one was asking, well, you know, the trip was about like 500 miles, right? But why don't we have any fuel anymore? Yeah, you know, the guys who planned that in the office were actually French, and they planned for 500 kilometers and not miles. So they were in the middle of the desert, stranded, and no fuel. So yeah, okay. Yeah, so these things happen. You have to be very careful because it's a great way to introduce errors, in particular when the columns are not annotated with a unit. Yeah, you might make an assumption of the unit, I guess it's kilogram. Why would it be different than kilogram? Oh no, it's per 100 grams. Oh my gosh, that's a weird unit. Yeah, so be careful, otherwise your queries will be returning crap. Yeah. So what do we show here? Calories per household and months, order by calories. Yes, per household and months. So I think we have 180 days or something like that in the database, and so for each month now we compute the calories being that were purchased in the household. That's not enough, of course, because maybe there are more people in some households than in others, so that number alone, the sum is not enough. So I still have to divide by the number of people living in that particular household, of course, to get a meaningful average. And that happens then here. So that's a different grouping. It happens here in the next block. Yeah, so here basically then have to look at the number of inhabitants, and I think daily constant per inhabitant. So here we go. Huh? So here they have the household ID, then you have the number of inhabitants, and they have the daily calories, and then we have the daily calories per inhabitant. So here's only one inhabitant, this divided by one is the same number, yeah. But then basically you can order that descending, and then you get outliers like that. You say, okay, this is like double something, or this is really an outlier with respect to the data, with respect to the other households. And that's basically what's shown in the book. Yeah? And that's basically the query idea in the NSA book by Eschbach. Yeah? So here we do some more machinery. Now we compute, okay, what are the daily calories per inhabitant anyway? So basically you can compute an average. So what do inhabitants eat on average? Yeah? So it's basically compute the total calories consumed versus the number of inhabitants, and then divide the two numbers, and then you get an average. Yeah? So what could be wrong, or what could be an issue with that average? So I compute, so I have the purchases. I know how many calories were purchased. I know how many inhabitants I have. I divide the two numbers, total calories purchased in the 9 months divided by number of inhabitants. It gives me the average calories eaten by each inhabitant. What's wrong with that? Yeah?
What if some food was thrown away?
Very good. What if some food was thrown away? The question is that a big issue? Not sure. Some households throwing away more food than others are more wasteful. Yeah, maybe that's the reason they have a 7,000 there, because they're too stupid to plan their food and they have money and they don't really care and buy all kinds of stuff and throw it away. It's an absolutely fair explanation. Yeah, could be. Other suggestions? Yeah?
What if there is elderly or children who don't eat too much? And
Right, yeah.
grown-ups who eat like a lot, like half, then the middle number will be not representative of any of them.
Exact. That's actually when you scroll down in the notebook, there's an extension to that where we do that, where you factor in age and babies and stuff, and then you can adjust your computation. Absolutely right. And I think in the example we also show a second household then that shows up. Yeah. Other problems? Yeah. Like to? So to grow food, you mean? To hoard. Okay. Yeah, that's another interesting point. Yeah, so you just buy like crazy. Yeah, and put for bad times. Yes, for like to be ready for whatever the next flood in Saarbrücken. Yeah, fair explanation. Very good. More.
Maybe some households regularly throw like parties where they invite other people over. And there are more people that stay.
Yeah, so some people might eat in different households actually, right? Yeah, very good explanation. So if you throw many parties, you buy a lot of stuff, but you don't eat the stuff yourself. The people living in that household don't eat the stuff themselves, but other people live. Yeah? Maybe actually you can detect the party goers. Those are the ones that don't buy too many calories, but they always hang out at different parties, right? And eat there. Yeah, very great answers. More ideas, yeah?
Does it account for eating at restaurants or at fast food? Maybe not.
Yeah, restaurants, right. That's a similar instance of that class to say, okay, there will be use cases where people buying the stuff don't eat it. No, not the people in the same household will eat it, but someone else, like a restaurant. Very good. Yeah?
Some people could live in more than one household.
Yeah, we kind of forbid that as far as I remember from the schema. So that's what this so period of time and citizen implies a household. That is the idea here. At any time you only have one household registered. Of course, that could be the official thing. Unofficially, you always stay with your girlfriend anyway and eat there. Yeah, so the assumption would already be broken. Yeah, that's correct. Yeah, more ideas. Any other problems? Yeah? Louder, please.
If you're doing this for figuring out if people are hiding in a household and do it for a time period where people are already hiding, then the calories consumed by that household will already include these additional sort of people that are hiding, right? So you won't be able to kind of...
Exactly. Yeah. So this is computed with respect to the registered 40 inhabitants, but we might be talking about more the hiding people, right? So that's not the true average. That's the average with regards to the registered people. Is that what you're saying? Yeah. Okay. That's true. That's another thing. Other things? I think we had many already. Yeah.
Some people could shop for multiple households. For example, you will shop for your parents as well, or grandparents.
Great, good. Yeah, you go shopping, and but that's for different households, for your parents and friends and whatever. Yeah, so many things where these things could break. Yeah? So always question your assumptions, in particular with data and computations, always question that. Still, even factoring in those problems, you can detect some people with that kind of query. Yeah? That's the problem. Yeah? So it's not perfect, but it gives you some insight. Okay. And that's basically explained in the book. Then basically this one stands, here this one, where was it? This stands out, yeah, for instance, but then there's more analysis in the notebook where we show that, yeah, if you adjust, for instance, for babies or kids that eat less, if I remember my kids, they don't necessarily eat less, I wouldn't, yeah, but could happen then that you find other cases. Okay. So there's so much about that. I think we were here. So take a look at that. So we will now look at what ethical problems arise from these kind of data collections and how do we deal with them. So in Eschbach's book, the main character, Helene, an NSA employee, conceives various SQL queries and thus helps to find hidden people. And it's clear that without Helene's work, many of those people would probably never have been found. So she actively helps the regime to find those people. But what does that imply? What does it mean for Helene's work? To a large extent, this is already explained in Eschbach's book. With the various queries, Helene also finds her lover who is hiding. But the key question is, what would have prevented these people from being found? What could Helene have done? And we will look at some possible solutions and ideas in the following. None of the following is to be understood as instructions for action. Some of these actions are punishable by law, depending on where you work. So we're just discussing it in principle, what possibilities for actions Helene or anyone else would have had in the context of civil disobedience, civil resistance in a comparable situation. I'm not suggesting you do it like that. That's your decision. I'm just saying those are possible things you could do. So there are a couple of technical approaches first. So one is, in German, it's a nice word, Datensparsamkeit, in English, data economy. The idea is to create less data. Yeah? Only create the data that is required or try to avoid creating data. The data that wasn't created cannot be analyzed. It's that easy. Yeah? So this works in certain situations, but in the book, for instance, there's this problem with that they don't have cache. If you don't have cache, then everything is electronic. For every payment you make, there will be a record, and those records can be analyzed. I mean, that's a big discussion in many countries. Okay, should we really get rid of cache and don't just do everything electronically? So there were some proposals like that. But for cache, you cannot necessarily track what you did with a cache. In contrast with a transaction, you can. So so I would be in favor of keeping cache and not having everything electronically. And that's a big assumption they do in the book, to say, hey, no, everything is electronic and therefore you can track it. Store only a few attributes. So for instance, to show that I have bought something, I do not need to disclose what I have bought. The question is, what do you want to model? What kind of information do you want to keep? That's a typical error in modeling when you come up with an entity relationship model and then the relational model. Which attributes do you really need to support your application? Is that really something anyone would be interested in? Is that something that might pose a risk eventually for someone? So there's a very famous example and very unfortunate example that was from the census in the Netherlands. They did that, I always forget that, in the 20s or 30s, before the Nazis invaded Netherlands. They collected census information about religion. Yeah, and they collected information like, okay, Jewish, Christian, stuff like that. And that record fell into the hands of the Nazis. So the Nazis knew directly when they invaded Netherlands, okay, who was Jewish and who was not. Complete disaster. Yeah, and that led to deportations of more Jews, as far as I know. than in any other country. Yeah? Complete nightmare. So that's a problem. Yeah? Why do we have to keep information about religion? Or, I mean, for instance, why do we have to even keep information about gender? Gender, race, or religion in any system? Is that something that, I mean, why? Yeah? Just because everybody does it? Everybody asks for these kind of attributes of your person? But if in doubt, don't collect that information. Yeah? It's that easy. So for modeling purposes, the question is, can I restrict the schema beforehand? Yeah, and that's what we do in data modeling anyway. So data modeling is about abstracting things, throwing things away. We don't keep each and every attribute. We just keep the attributes we're interested in and that makes sense for the context of a particular application. No? Okay, this works to a certain degree. So some attributes you still need, and these attributes may pose risks, of course, but you should at least think about that when modeling. Is that really something I need? Yeah? Or is it something I don't store in the first place, so then it can't become a problem later on? No? Yeah, anonymization. Yeah, that was something people believed would work. So anonymize search queries in the search engine, for instance, there was a very famous case of the AOL search query log. So I'm not sure whether any of you still knows AOL. It was a search engine in the 90s. And they had this infamous idea to publish a search log. So basically the search queries people entered into the search engine for a certain period of time. And I think it took like, I don't know, less than a day to identify some of the users. Yeah, so there were no usernames. So they were just, I think it was an ID and then the search query or something like that. But what happened, for instance, some people just search for themselves. Yeah? I frequently search for Jens Dittrich. Maybe some of you also Google whatever your name. And that was present in the data set, something as stupid. Yeah? And so a couple of users were quickly identified and then more and more, so it was a real privacy nightmare for AOL. And there's an article about that in the New York Times if you're interested. Yeah, then there's encrypting data. Of course, you can encrypt parts of the data. And then the question is, okay, is it just the attribute value? Is it an entire tuple? Is it a table or the entire database? But then the problem is that you can still break these things for certain situations. Yeah? So for many of these measures, it's actually like that. It's not the perfect solution. So there's basically never a perfect solution avoiding all of the issues. However, many of these things make the life of an attacker more difficult or make it less likely that problems will occur. And that's basically the spirit in all of these approaches, that they say, yeah, if you try to do as many of these things as possible, and then it will become more difficult. Yeah? You can't completely avoid problematic situations, but you can avoid many things. Yeah? So anonymizing, encrypting parts of the data. Next is make joins difficult. Remove possible join keys. That's the most important thing. Yeah? So here in the book, it was a uniform citizen ID. And again, there are proposals out there where in Germany, where people propose something like that, a Bürgeridentifikationsnummer. Once you have them, that you're in trouble land. Then you can do these joins across different databases. Yeah, it might not be a problem in a democracy, but yeah, if the political system changes eventually, yeah, the same things may happen. Yeah? And so that's a problem. You should avoid these kind of things. And a good example how to avoid these problems is the so-called Corona Warn app. Yeah? I'm sure, I know I shouldn't say the C word anymore. Here no one wants to learn about Corona anymore. But there was a great application. It was a Corona Warn app that really did it right. Yeah? So I'm not sure whether you remember, but it was basically on your cell phone. The idea you would have the app running, and via Bluetooth it would detect other smartphones that were close by, so you can measure the distance to other smartphones and then collect certain keys. But that was done in a way that it wouldn't violate your privacy, in contrast to another app that existed that was a Luca app that did everything how you should do it in the opposite way. Everything was done wrong in Luca, basically absolute nightmare, completely terrible. And the data from Luca, for instance, was also used by the police. But the data was not, they were not allowed to use for those purposes, and the users probably didn't give their consent for that. So long story. But that was impossible in the Corona OneApp. You simply couldn't do these kind of queries. It was impossible, technically impossible. It was done in a great way, and that's why I would like to talk a little bit about that. So it was developed since 2020 when the pandemic started as a cooperation from SAP SE and Deutsche Telekom, and it was highly decentralized. And the type of query processing and data processing was done in a way where I would think immediately as a database people, oh yeah, that's really completely stupid. Why would you do it like that? But when you think about it twice, no, that's actually super smart how you did. Sorry, I'm so sorry. Sorry, this is awesome, right? Yeah, so they trade query performance for privacy guarantees. And that was a cool thing. Yeah? So given the computational power you have on a smartphone, they said, yeah, I don't care. I mean, you have so much power here. Why would I worry about query processing? Privacy is so much more important. So we do something really insane in terms of query processing, which could be done so much faster. But if you did it faster like that, then you would compromise privacy guarantees. Yeah? And that was the cool thing about that. So the idea, again, was something like that. So the smartphones measure the distance to other smartphones via Bluetooth. Details don't matter. You had a way to do that. If two smartphones fall below a distance for a given period of time, both smartphones would record that as an encounter. And of course, the naive way of doing that would be, yeah, there's an ID, a fixed ID for my smartphone. If I get in touch with whatever your iPhone, yeah, your ID is recorded on my iPhone and my ID is recorded on your iPhone. And later on, you can use that information to do query processing. So if I get Corona, all the IDs that are on my phone could be informed easily. Super easy. But that's not how it was done. So it didn't use persistent personal keys, but rather temporal keys. Every smartphone generated a new pseudo-random key every 15 minutes. Only those were exchanged. So every 15 minutes, you would have a different key. Yeah, it was also not that you had one temporary random key and kept it for a long time. Now every 15 minutes would be a different key that you would exchange with other people. And then basically all users regularly downloaded the keys of all those tested positive and intersected them locally against their own keys to determine the risk. So how did that work? So if you, every 15 minutes, issued or sent another key, and now we would be in contact. Yeah? Now you would collect my temporary key. That's it. Yeah? Maybe half an hour later we would meet. You would collect another temporary key on your smartphone. What you would do with your smartphone app was you would contact this. So if I get Corona, I would inform the server, but by not telling the server my name, but just sending the set of temporary keys I issued to the server. Yeah, so the server would know the set of keys, also very long keys, of course, yeah, the set of keys that I issued while I was potentially contagious to other people. Yeah, so the server collected a huge set of keys for all of Germany, basically. Insane amount of information. But as I said, yeah, in terms of query processing, not so smart. In terms of privacy, awesome. And then you would regularly, on your app, download that set of temporary keys, and the app would check whether you had an encounter with any of those. Yeah?
Everybody needs pseudo-random keys, and we want to make sure that there are no collisions between the keys, correct?
Yeah, those are cryptographic keys.
How do we make sure that the keys don't accidentally collide between users? Because that would cause a lot of problems, and wouldn't that practically also make the randomness lower again?
Yeah, there are ways to create keys where basically the probability that you have a collision is like insanely low. The cryptographic hash functions are used for that. Yeah, so in principle, you're right, it can happen, but you can generate those keys in a way that's basically a no issue.
But we would have to take into account that it's possible that such a collision.
I think you can ignore it safely. It's so unlikely you can ignore it. Yeah. But ask your local cryptographic expert on that. Yeah? But the bottom line for you is you can generate keys in the way that collisions are non-issue, yeah, in this setup. Yeah? So where was I? Okay, so you download the set of keys from the server on your app and see whether you had intersections, and depending on the number of intersections, the app would then switch to a warning, would issue a warning. If there were no intersections, it would say everything is fine, and then depending on whatever 3 intersections, it would issue, hey, be careful, 10 intersections, hey, maybe you should see a doctor, stuff like that. That was the idea. Yeah, so there was no central query processing. Everyone processed the set of temporary keys locally on their smartphone. Yeah, what a great idea. Yeah. And yeah, that's basically the entire approach. And that's actually, we did a notebook on that. Maybe let's briefly switch to that one. I mean, I do a certain simplification, so the ways how the keys are generated are a bit more involved. Yeah, but for making the point, the notebook basically shows a core idea. Yeah? So I need to define those key sets. I need to define this notification server, basically from Robert Koch Institute, yeah, where these keys are collected. I have to create those users, and then I have a couple of users that are, maybe I'll just show it briefly, that are running around. Yeah? And then basically, whenever the distance between 2 of these users falls below a certain threshold, they exchange their temporary keys. Yeah, what I just explained. So you keep this, so you have an encounter like these 2, for instance. So they obviously are very close, and they exchange temporary keys and make it part of their key set. You also attach a date to the encounter, of course. So if I think it was like 2 or 3 weeks. After 2 or 3 weeks, you would discard those encounters. Yeah? So it was just relevant for a certain time interval. Yeah. So and here you could now inspect, what I could do here now is I could look at the data. So for instance, so this is something I wouldn't be able to do in the real application, because this is, so only one part of that. So this is per smartphone. Each of those entries is one smartphone. So you see it, that is just an ID, the name of that user. That is the current key that would be issued. That is the own keys issued at that day. Those are the encounters on that day of particular keys. You could also attach how long the encounter took and stuff like that, could refine that, but that's the basic idea. But already producing this list is impossible, because in the real application, because only inside the app you could access the data. Yeah? But there was no way for Robert Koch Institute to like query the different Corona warn apps. Yeah, so basically here is see what happens collecting these keys. Right. Now we assume that one of the persons gets infected, made a test, and now wants to inform everyone about this. Let's pick one person randomly. That's what I'm doing here in the code. So that's person number 19, picked randomly. This person now informs the server about the positive test. Yeah? So in other words, it sends its temporary keys to that server. That happens here. Now we can see what the server sees. Those are those temporary keys from an infected person that are added to that huge set, saying, okay, on that day there were those temporary keys from a person that might have been contagious, so might have posed a risk to someone. And now every person that uses the app regularly checks the status by downloading that key set from the server. That happens here. And then you can basically check the status. Yeah? Here again, I'm doing it for each and every person. Of course, you would also only do it on your smartphone. Yeah? You could only determine the risk for yourself, but not for anyone else. Yeah? And then basically, depending on the number of encounters, in other words, the number of keys you find, the number of intersections you find in that set, you can issue a warning like medium, you better get tested, high, yo, self-isolate now, get tested now, and so forth and so forth. Yeah? So that's the entire idea, and I also visualized that kind of basically here I think orange was, orange is like, yeah, be careful. Red is, oh, you had so many encounters, get tested and self-isolate. That was the idea of the Corona Warn-App, and it's a great example of not using keys that can be joined. Yeah? If you don't have those join keys, you can't reconstruct the data, and you don't have that big data problem that you join across different tables and deduce information that was not intended to be deduced. Yeah? And this design principle is really nice in the Corona Warn-App, and you should keep it in mind. If there's a situation where you can apply that principle, do it, because it's a great idea. Yeah, questions about that? Yeah?
So in half an hour, if I'm speaking to some person, it will count 2 encounters?
Yes.
Because it will just
Yes. Yeah. Right. Yeah, whenever you issue a new temporary key, you then also collect the next, and that would be counted as 2 encounters possibly. I'm not sure whether they had a means to detect that those 2 temporary keys were issued by the same person. Not sure. You could fix it. You could do that if you wanted. Yeah. Yeah. But in theory, yes. Yeah. Other questions? Okay. Okay. So some more technical approaches. Differential privacy, that's a term you might have bumped into. So what you can do is, if you have a database, you can introduce artificial noise. You can add small errors to the data so that analyses are only partially falsified. So you can make certain types of analysis impossible. However, that is relatively hard to do from what I heard. And it's very hard to decide how much noise should you add to falsify certain analysis and not falsify others. Yes? So it's tricky, and I think you also need to know the queries in advance and stuff like that, so it's not really something that helps. What you can do more easily is you manipulate the data. Yeah? Change data so that queries do not longer show certain results, and that's actually done in the book by Helene. Modify certain tuples, that certain things are not joined anymore, that certain things don't show up. For our calories example, you can go to the purchases table and decrease the number of purchases for a household, for instance. Yeah? Maybe no one notices. Yeah? I don't know. That's things you can do, of course. Anti-hardware administration, how I phrase it. So you manipulate, disrupt, or slow down the hardware. So unfortunately, the server is down again. I don't know what the problem is. That's also done in the book. So in the book, there's always this data silo. That's basically a fancy term used for a hard disk or an SSD that is slow. So if her boss approaches Helene and asks, hey, where's the results for that query? Helene says, yeah, we have a technical problem. This data silo is slow, blah, blah, blah. And the boss can't check back. Yeah? There might be workload peaks. There might be water damage. So these things can be done, and sometimes are hard to track. Yeah? So the more complex the setup is, the more complex it will be to detect that. Docker is your friend. Virtualization is your friend because it's so complex that it's hard to track from the boss, I guess, that you manipulated it. And then these kind of excuses where you say there's nothing we can do about it, it simply takes that long. So you could produce unmaintainable spaghetti code. Most of us do that anyway, by default. Yeah. So if there's a bug, people can't track it down. If the people who wrote the code are not there anymore, maybe you break the entire the production system. You might include hard to find errors for these cases. Concurrency is your friend again. So they're so hard to track. Maybe you can bring down the system. You might write complex queries that overwhelm the query optimizer. That might actually happen if you know what you're doing. If you, that's more an advanced database topic. But if SQL makes certain things, gets too complex in certain directions, some database systems will have issues with that. There's always a database system that can handle that. But if you do it the right way, you can overwhelm the query optimizer and make everything slow. This also is true for using the wrong database system. There are, I don't know, about 1,000 different database management systems out there. If you pick the wrong one, you're screwed. You can configure the database system incorrectly to make it slow and then produce crappy results. You can use NoSQL, JSON, or XML that will slow down everything dramatically, so that's a great idea to use that. You can write code that has quadratic or worse runtime, and that's also a common error you see in projects. Sometimes you test with small data, and then you don't see that there's a quadratic or worse complexity going on, and then once you start adding more data, you see, oh no, this is really getting slow, what's going on? Yeah? So do not document the code at all or document it incorrectly. That's also fantastic. Another default you see in software engineering very often. If you don't document your code, okay, now there's ChatGPT, of course, yeah, but that makes it hard for people to track down what's going on. Yeah, then there are these social approaches also used in the book. So excuses for Melina, this query is more complicated than I thought, I need more time. It's not that simple, we should still consider aspect XY. We don't have the right software, hardware for that. We first have to buy XY and organize training, deploy XY, blah, blah, blah. Yeah, so this is impossible to track from a manager who is technically doesn't understand what you're doing. For this, we should call in Mr. X. He's an expert in the field, whereas in truth, Mr. X is an idiot and will most likely slow down the project. Yeah, we can use that pattern. We should delegate that to department Y. They didn't get anything right in the past either, so it's the same approach, just on the department level. The project is too big. We should divide it into sub-projects so that afterwards no one has an overview and we lose time in pointless meetings. Yeah, that's another also common pattern that is used, not intended to ruin a project, but you see it often, it's split up and you do meetings and don't do real work. Then there are legal approaches. Questions? So we prevent joins, make access to multiple data sources difficult, no data cartels. Yeah? Don't put databases into the same silo. Don't combine databases. Don't make it disallow joining of different databases. That's so important. So restrict access to sensitive data sources. And then, okay, what the heck does sensitive mean? That is very hard to predict. Prevent certain types of data sources from being brought together. Yeah? So we looked at that in the technical approaches. So prevent joins across databases. That's basically the main thing to keep in mind. Yeah, but what are the sensitive data sources? So one is temporal. If there's a temporal dimension that smells like sensitive, a spatial dimension. I'm not sure whether you heard about this. There were so many incidences with spatial data. Now with smartphones, you keep the position of the smartphone, and that's recorded in various apps, including Google and whatnot. And I think there was one for an app for runners that was used by military personnel in the US. Yeah, and they used that to run. And with the data, you could visualize hidden army bases in the US. You could see, oh, all of them are running there. It's pretty weird, yeah. And I think the US Army didn't want that to be published. So, and yeah, these kind of things, yeah. Also, profiles in general, in German it's called Bewegungsprofile, spatial profile. Where were you at a certain point in time? Yes, in particular for that can be used to understand who you met, what you did, where you were, and also in criminal cases can be used to in your favor or against you. If you can prove with such a spatial profile, oh, you were there when the crime happened. Yeah, that's on your cell phone data. You don't want that. If your cell phone data says you were not there, I can prove it with the data. Yeah, that's cool. Yeah, that is actually really helpful. Yeah? But it can go either way. Yeah? So temporal and spatial smells risky in general, but it can also happen for other data sources. I'm not sure whether you go into this one. Yeah, I think we leave that for the exercises. But the main thing you should really keep in mind is it's like a criminal investigation. So if you remember what criminal investigators do, yeah? So they have a blackboard and then they have a picture of that witness and then the victim and probably the criminal, and then connect it with threads. Oh yeah, there's basically they build a graph. Yeah? You've seen that in so many movies. That's basically joining information from one part to the other manually. So these detectives basically build a database on the blackboard/whiteboard and then join the different pieces of information. And that's very, very error-prone and cumbersome and awkward, a lot of work. What databases do is with joins, they do that automatically with huge amounts of data. And that's the problem here, is that you can reconstruct and connect the dots among seemingly independent pieces of information. Yeah. Right, what do I have here? I think we skip over that. I think there's one thing I wanted to add here, because that's really, you might have noted, where's that? Because Datensparsamkeit. Right, so Datensparsamkeit, I forgot something that's not on the slides here. So the less a society is digitized, the less digitization you have, the better you are prepared. Do you understand what I'm trying to say? So Germany is at the forefront of protecting your privacy because we fail so hard in digitization. Yeah, keep that in mind. I mean, there are many rankings in digitization where we see Germany is, if we are good, we are on the second to last position. Yeah? Typically on the last position with respect to Europe. Yeah? So they're really prime examples for digitization, like the Baltic states. There you have an app, you click once, and that's your tax declaration. One click with a button. Yeah? In Germany, impossible. It takes hours. It's for me, I don't understand my tax declaration. No way. Yeah? You need a consultant. And for many other things, Germans love to use paper. Yeah, we print out things, we print forms. It's important that we print it out and sign it with a ball pen, send it somewhere by snail mail, someone replies, faxes it somewhere else, asks back. So there are many people involved in administration, and the Germans are very reluctant to digitizing these kind of processes. You see it all over the place. You see it also here on campus. There's so many examples on that. And whenever you touch any administrative issue in Germany, you will see what I mean. And that is, of course, bad because it makes it awkward for you to do certain things. On the other hand, it gives you a certain degree of protection. Yeah, because it is basically an example inadvertently for Datensparsamkeit, for data economy, because if the stuff is still analog, you can't that easily track it. You can't that easily do surveillance and these big data things on that. Yeah? So that's a side effect. So everybody's complaining about the failing digitization in Germany, but actually it has also this one positive effect that I wanted to mention. Yeah, just to mention that. Okay, what else can I say? So, the question we looked at, what are the ethical problems that arise from these kind of data collections? How do we deal with them? So there were a couple of solutions. There are many possible countermeasures, both legal and civil disobedience. In principle, the joint evaluation of several data sources / database joins, SQL joins, relational algebra joins should be much more strongly regulated. Monitoring through metadata, which is also often processed, video or audio data, can reveal surprising correlations. So what I mean by that is, of course, you can like annotate the video, yeah, like in pictures, you annotate, okay, that's person X, that's person Y. That is the metadata, and then that metadata can be analyzed by the database system. So database systems typically don't look directly at video or audio data, just the metadata extracted. And those correlations can reveal surprising correlations. Those types of analysis can reveal surprising correlations. So. And yeah, the problem of this is this can be used for bad. See the examples above, as well for good. Also, so data journalism, we will look at that later on. So I will show another example where that was used to analyze graphical data. But the underlying problem is always the same, and that's super difficult to solve. What if data gets into the wrong hands? You know? Because you cannot predict what may happen with that data. So, yeah. So for the next weeks, 2 weeks, we will look at question 3. So what if the data gets bigger? How do we actually get from SQL to an efficient program? So how is SQL translated into efficient program? That is the next 2 weeks. Next week is a holiday, but then the 2 weeks afterwards. Then we look at IMDb part 3, where we look at how do we use a database system in a web application. And along in that context, you will also start with a project. As I said, at the beginning of the semester, we flip 2 assignment sheets into a project. So you don't have assignment sheets in those 2 weeks, but we ask you to do a project. And that's another example of how profile information can be used for good. Yeah, so whenever people say, oh, profiles, that's bad, yeah, social scoring in China and whatnot, and spatial profiles and stuff like that, yeah, this is super bad and super risky, you shouldn't do these kind of things. But there are types of profiles that can be used for good. And the project you will be doing in this lecture is an example for that, where profiles can be used for good. But we will get there in a couple of weeks. So there's more material if you're interested. So I had already a couple of pointers in the first part. So this is the biography by Edward Snowden. It's super cool, very interesting. I really recommend reading that one. Glenn Greenwald was the journalist who worked with Edward Snowden. So Edward Snowden didn't reveal the stuff himself, but he gave all the material to Glenn Greenwald, who then unveiled the stuff. It's also interesting. If you think like there's no surveillance in Germany happening, well, then read this book. That's a professor of history from Freiburg who wrote a book about surveillance in even before the unification with Eastern Germany. This video is super cool. That's by the author Tom Hillenbrand. He reports on very early attempts to surveying letters that happened in 1684 rather than 1984. Already people wrote letters on paper at the time, and there was quite a machinery to open those letters, read the letters, create copies of those letters, and then close the letters such that no one would detect that the letter was opened. It was quite a machinery. It was also time sensitive. They had to be very quick, and then they had already centers for opening those letters. So it's a very nice video if you're interested. In general, this is the bibliography for the lecture if you're interested. Yeah, and that's it already for today. Any questions? No. See you in 2 weeks.